So now introducing Steve Theno. And Steve, I believe you're going to talk to us today about NewMars and the new concept for 1,000 person month.
You bet. Thank you very much. Well, as you just heard, my name is Steve Theno. Really pleased to be able to be here today to give a presentation to this group. Actually, just to be here and participate in the Mars community. So far, it's been a great experience. I am going to give my presentation will be about the concept design for proposed utility systems and nuclear life support systems for a potential first colony on Mars. It's a concept I developed as part of a larger project, which was to enter the Mars colony competition. And my entry into that was called NewMars. But for this particular talk, can you speak a little bit louder? I'll try. Thanks. Is that better? That's all right. No, I think I'll try just speaking like this.
Appreciate it.
Okay. And but anyway, for this presentation, I'm just going to focus on the engineered systems, utility systems, and life support systems. By way of background, I'm an engineer, mechanical engineer, retired now. But during my professional practice, I focused mostly on planning and design for a pretty broad range of facilities, primarily in remote cold regions environments. And get to the technical program. One of those environments that I had the opportunity to do some engineering at was the Amundsen-Scott South Pole Station. So the inset that you see is just a quick comparison of some of the challenges and environmental factors that we faced in developing a design for South Pole Station, and I tried to compare it to a potential site for NewMars. And what I took from that was that a lot of the experience that we gained in developing a design for Antarctica, for South Pole in particular, probably applies to at least the concepts that we might develop for a practical, sustainable facility on Mars. And we also, I tried to take into the development of the concept design some of the practical strategies, which are shown on the left there, that have worked well in those remote cold regions environments. So applying proven technologies, not necessarily rocket science, but proven technologies, to really apply practical design solutions, blend in a little bit of creativity with it, and above all, design systems that are really flexible to adapt and change. Because there's going to be a lot of new developments before we even deploy. There's going to be a lot of learning that occurs, lessons learned once we're on site there. So you'll have to excuse me, I had two different versions, and as luck would have it, I selected the wrong one. But I'm going to have to skip through a couple slides just so we make it through. Okay, then I'm going to speak, as I mentioned, particularly about the technical solution. The particular systems that I want to discuss are on the lower right. Those are traditionally the primary utility systems, life support systems, environmental control systems for any kind of facility or settlement that would be in a remote region. And then the technical criteria that's presented on the right, not going to go through them, but again, those are some of the practical approaches that have served us well in developing design solutions for practical systems in other remote locations. And I tried to take that same principle into developing the systems, potential systems for NewMars. So we'll take a look at the first set of systems. Those are the energy systems. So obviously a NewMars colony is going to need, critically going to need electric energy and thermal energy systems if we're going to be successful at the colonization at all. So the first step I took was to take a look at all of the typical previously proposed energy sources that might be applied for a NewMars colony. And then I tried to integrate those, select from those, and integrate those into a solution for NewMars that best fit the characteristics of NewMars. So this is the solution, concept solution that I came up with. Basically, it involves creating 3 energy centers that would be distributed around the circumference or perimeter of the colony. Within each one of those energy centers, we'd have a mix of PV solar, micromodular reactors, and very small modular reactors as the primary power generation source. And then we would network those energy centers together with a duplex, basically AC electrical grid, and then we would serve specific loads through load centers that are established at the locations of the actual demand on the electrical. And the purpose for that approach is to diversify the source of electrical energy requirements and provide a really robust, redundant, reliable system, and also a system, since it's composed of multiple parts, a system that has the ability to adapt and change and grow with the development of the colony. And then from the thermal energy side, the primary energy system we selected for electrical has, as a byproduct, significant quantities of waste heat. So the NewMars colony is going to require significant thermal energy input, and we're going to harvest it in the form of waste heat from the electrical power generator. So this is a distribution diagram for the thermal energy systems. It pretty much parallels the electrical. At each one of those energy center locations, we're harvesting the waste heat off the power production. We distribute it throughout the colony with a duplex, probably fluid-based thermal distribution grid. And then at load centers, again, we tap that distribution grid to serve specific requirements at the conditioned space. And when we tap that distribution system, we do it with heat exchangers or other devices that can decouple it from the primary distribution system, so we don't create a situation where there's a potential single point of failure that could bring the entire system down. And then once I have the energy system selected, I took a stab at penciling in basically a first cut energy budget for a 1,000-person colony. So the top line there is the core conditioned space, and I came up with a load that would be about 2 megawatts. That's about 2 kW per colonist, basically. And there's some data points that kind of support that. The U.S. average now is about 1.3 kW per occupant. McMurdo Station, which is the largest U.S. station in Antarctica, has a summer population of about 1,200. They operate at about 1.8 kW per occupant. And then South Pole Station, which is really the more extreme environment, and the power demand there is swayed because of the research loads, because that's a research station. That runs at about 4 kW a person. So I thought 2 kW a person to pencil in as an energy budget for the first colony on Mars would be a challenging, hopefully conserving approach, but a realistic one to meet the needs of the colonists. And then there's a couple of variables, a couple of additional power requirements that we have to look at seriously to add into that. And we're going to talk about water supply in a minute. That's one of them. But the other one is food production. We'll talk about the food production approach that we have for NewMars. But we're really, realistically, looking at a range of power demand from somewhere between 4 and 30 megawatts. So it's a significant electrical energy demand for that food production. So the other takeaway from this was, one, it kind of established, at least in my mind, the magnitude of the energy demand that's going to be required for the colony that we would have to produce. And then in addition to that, it kind of demonstrated the value of the choice we made for those power supply units. We're really going to have to lean towards portable, modular, nuclear energy sources initially in order to get a colony up and running and meet the power demands that we really see. Okay, so I want to go on and talk about water supply, probably the second most, if not the most critical utility that we have to be able to meet with a NewMars design. And I took the same strategy. I looked at the traditional water supply sources as identified in the various, in the public domain there that might be applicable to Mars. I added one which is recycle and reuse. It's not really an in situ resource, but it could be a viable approach to creating an effective design for the NewMars station. I looked at all 4 of those sources then, and the one I selected as the baseline system for NewMars was to basically harvesting ice crystals from the regolith. And the reason for that is that it's very high probability that it's going to be there, so we've got a resource we know we can count on. And the second thing is it's really independent of the location you might select for the colony. So there's lots of reasons, lots of factors that go into optimizing that colony location, and at least we'll know that we can achieve our water resource needs irrespective of the location we pick. Otherwise, it's a pretty straightforward system. We'll have multiple harvest extraction sites around the colony, multiple for, again, reliability and robustness. We'll harvest those to the greatest extent possible. We'll try and use solar energy to help drive that water recovery process. And then again, I did, since the baseline approach is going to be a very resource intensive, very energy intensive baseline for getting the water supply for the colony, then I did roll in the recycle and reuse. And typically those are high energy approaches and fairly complex approaches, But in this case, I think it's warranted if we're really going to have a sustainable Mars colony. Okay, I'm going to skip this one just from a time standpoint. So then I want to take a look at wastewater treatment and disposal. So the primary sources, obviously, for the NewMars colony would be human sources. And generally we broke them down basically into two categories: gray waste, traditionally gray waste, and black waste. And once you have the sources identified, there's really two typical treatment process paths you might follow. One is physical chemical, one is biological. Both of them are mature technologies on Earth and have been applied in a lot of remote locations successfully. The physical chemical is generally associated with smaller systems and is generally considered to be high energy and high complexity and high maintenance. And then the biological is probably much more familiar with larger volumes, although they can be applied to treating a wide range of waste streams, and is generally considered less energy intensive, but I included high maintenance there because in my experience, in spite of what you might hear, they tend to be finicky systems and relatively high maintenance. So we'll select between those two different approaches to the waste treatment, and then ultimately we have to decide to what degree we're going to treat, and the degree that we're going to treat is dependent upon the decision as to whether we're going to dispose of it or we're going to try and reuse or recycle it. And that's usually driven by the resource and energy requirements of the water supply itself. So this is the system that I selected for this hypothetical NewMars, and it does rely heavily on recycle and reuse. Basically, I separated the gray waste systems and plan to put in a physical chemical recycle treatment system for that. Those treatment systems would generally be smaller in size. They generally be located at the sources where the waste is being generated. So you've got a distributed treatment system that adds in some built-in reliability and redundancy. Then I'd separate the black waste stream into the urine side and the traditional water closet black waste. The urine, which can be relatively easily treated for certain uses, would be treated with a physical chemical system, and that would be used in crop production for fertilization. The black waste would as well, but it's going to require significantly greater degree of treatment, and then ultimately composting, and then we'll batch apply that for fertilizer and crop production. So the approach here is to maximize, recycle, and reuse. Okay, the food production system. So in our concept of NewMars, it would be agrarian-based, just for efficiency, and I think everybody here is well aware of the challenges with the Martian environment when we get into crop production and trying to do food production, and as well as the Martian soil. I think my takeaway was from the Martian soil standpoint, the good news is the minerals are there, the regolith can be processed to create a good soils base, so the materials are there, we just have to work it to be able to do the food production. Just like we talked about earlier, the utility requirements for water and energy are going to be huge drivers in terms of the type of system that we select. Now, a little bit of background in terms of deciding the magnitude of the food production effort. The upper left is just a brief statement of the infrastructure requirements for food production. So we're going to, no matter what food production methodology we take, we're going to be looking at enclosed environments to do the work. And because of the Martian seasonal cycle, we're going to be looking at probably bulk food storage to get sufficient quantities to run through to run through an annual cycle. And then because of the quantities of food that we're going to have to produce, then we're going to be looking at bulk food processing requirements. So that was the basic infrastructure requirement. And then I looked at the spectrum of methods under which you could do the food production in enclosed environments. Kind of at one end is the traditional greenhouse, and we generally consider the greenhouse approach as something that produces moderate yield. It's limited in terms of to just the growing season, but the real benefit is that it's a low energy user. We can rely on solar to accommodate that. At the other end of the spectrum, we look at totally enclosed, maybe vertical stacked farming and growth chambers, and the plus for those is very high density, very high yields, year-round production, but very high energy consumption rates. So those are kind of the trade-offs. And then to get an understanding of the magnitude of the food production requirements for a colony like NewMars, I took a look at production yields. So open-air soil-based farming on Earth today ranges anywhere from about 1 to 4 persons per acre per growing season per year. That's kind of the yield that we can classify. And most of it fits within that category. There's intensive cultivation efforts, aquaponics, hydroponics that take us out maybe in the 6 persons per acre per year range. And then there's lots of experimental work that are being done now that shows promise that perhaps moves that out into the 8 or 9 persons per acre per year. So for the purposes of developing a concept design for NewMars, then I selected, if we went with the greenhouse end of the spectrum, a yield that would be something like 6 persons per acre per growing season per year. And if you went to the other extreme and looked at growth chambers, you'd be up around 24 or 24 persons per acre, sorry. Okay, so that set the stage. So then here's the system that was selected for NewMars. I basically picked a mix of greenhouses and growth chambers. From a planting level standpoint, I picked a mix that's about 4 to 1. The ratio is about 4 to 1. And the purpose for that was, to the maximum extent possible, we want to use greenhouses. It's the lowest energy approach. But we also want the ability to have year-round fresh food production. The growth chambers offer that. So I picked the planting ratio of about 4 to 1. That resulted in a yield that's about 36 persons per acre that we might have under production at NewMars Colony. And the required square footage for that for conditioned space is about 2.5 million. So relative to the magnitude of the colony, the agricultural or food production infrastructure is going to be the significant footprint. Otherwise, again, we tried to stick with the concept of maximum conservation, maximum reuse. So we are using fertilizer and composting, as we discussed, from the waste system to serve the food production area. We would recapture the vapor emissions from the evapotranspiration process and recycle that to minimize the amount of water resource that we have to use, and then try to establish an environment that provides for high yield crop production. Okay, environmental systems. This is pretty straightforward. So I think the part I'd like to point out is within the conditioned space for NewMars, we selected an environment that we try and control to, which would be about 5% pressurization, 60-40 oxygen-nitrogen mix. Those gases are readily available. And that provided sufficient oxygen requirements for human metabolism. But beyond that, the nitrogen filler as the inert gas helped to control the flammability in terms of that particular environment. And then for any of the conditioned space, we already talked about the waste handling systems. For oxygen supply, the feedstock would be the water supply of the colony, and then we use electrolysis for the oxygen generation. In the case of NewMars, we distributed those electrolysis generators basically to the points of use, and again, that was to maximize reliability and robustness. And then, of course, the electrical systems and the thermal systems to satisfy the conditioned space would come from the central energy systems that I mentioned. And then the last piece we put in is, and I didn't talk about this under the energy systems, but in addition to the prime power generation, which is the nuclear supplemented with solar, then in addition we wanted some energy storage and short-term energy backup, and the source we selected for that was hydrogen-oxygen fuel cells. We basically used that as the energy storage mechanism. And those are located in the distributed energy centers for backup of the energy centers. And in addition, we distribute those fuel cells to the conditioned space, basically the load side. So if there ever was a disruption short-term in distribution systems or energy centers, you'd have immediate backup at the source of the conditioned space. And the nice thing about fuel cells is that in addition to generating electric, they also generate thermal, so it's inherent backup from the thermal distribution systems as well. Okay. I'm not going to talk about fuel production. That's just because of time, but it's a pretty straightforward approach looking at methane as the primary hydrocarbon fuel because we can generate it from the in situ resources. Okay, so that covered from NewMars' perspective the central utility systems and the central life support systems and the way we'd envision structuring them to practically and sustainably support a colony of 1,000 folks. So then I wanted to just spend a few minutes thinking about the colony layout. So this was an initial sketch of how the colony would be organized to support 1,000 personnel. We basically just divided the functions into sectors. It's laid out in a circular arrangement because the circular arrangement really facilitated adjacencies and simplified the logistics of traffic movement. On the left-hand side, you can see I've identified one of the energy centers. So there'd be 3 energy centers. They're distributed around the circumference of the colony, and that kind of optimizes the distribution links from the energy centers to the load points. And even as the colony grows, if it expands outwards, it still keeps a relatively optimized distribution link from an energy center. And then towards the top, in this kind of hypothetical site plan, towards the top is the residential area. And the residential area, we broke that out into clusters or neighborhoods for several different reasons I'll talk about in a minute. But also under this hypothetical layout, NewMars might be situated so where the residential area is located, it's a little bit of elevated, non-uniform terrain, so you get some nice views of the Martianscape, or try and roll that into the planning for the colony. And then this kind of lower right quadrant is the initial development of the food production area, and that actual sector probably extends out to about this distance at this scale. But one of the ideas behind the food production sector is we wanted the ability for it to expand out. We wanted it in close proximity to the residential sector because that's where our fertilization is coming from. And then initially we'd start out with fairly uniform sized greenhouses and growth chambers. But as the colony matured and as the ability to do value-added manufacturing on planet, then we could begin to shape those greenhouses to become more optimum in terms of efficiency of food production. And then the quadrant on the lower left is the inner quadrant really is operations. So that's like public works. And then out from that is an expanded area that's set aside for industrial and manufacturing, which ultimately is what would drive an economic base for NewMars or our first colony there. And then right in the center of the circle, that was what I call it, central services. So the idea behind central services is that administration, HR, education, healthcare, transient quarters, kind of the focal point of the colony itself. So this was another view potentially of what the solution would look like. And then similar to doing the energy budget, took a stab at penciling in what the programmatic square footage requirements would be for a permanent 1,000-person colony. So central services penciled in 30,000 square feet. This is from using data points, for example, like McMurdo Station I talked about in Antarctica, and South Pole, and some other remote, pretty much self-contained communities or installations that I was involved with in Alaska. The residential clusters, I talked about 4 clusters. Each would be about 100,000 square feet. So 400,000 square feet there. Commercial centers would be kind of the public space associated with the residential living area, and those would be integrated in with those residential neighborhoods. So I budgeted about 4 at about 30,000 square feet for that. Operations, that's kind of traditional public works level planning, about 100,000 square feet of conditioned space, really. So you add all that up, you have core conditioned space of about 650,000 square feet. And to compare it to a couple of other data points, I mean, that's about 650 square feet for colonists. Well, McMurdo Station, I mentioned, that station is being redeveloped, and under the redeveloped plan, they ended up at about 520 square feet per person. South Pole ended up at about 630 square feet per person. So you can see the similarity. I think it's, on one hand, a little bit on the generous side, on the other hand, it is a permanent living space for the colonists, so it needs to be diverse, comfortable space to exist in. I'm going to skip the construction phase. I would like to talk about this one just briefly. So this is just kind of the approach by which we would realize the development of the NewMars colony. So it depends heavily on being able to develop basically structural material, concrete material from the regolith. So we're processing, we're not bringing any materials with us, we're using all the in-situ resources. We would utilize IT and technology to the maximum in terms of producing it. So 3D construction printers, and then in the case of NewMars, we settled on using fairly basic, repeatable shapes just to keep that whole construction process moving smoothly. So that's kind of the sequence. The upper right's kind of the sequence. And then what we really hope would happen is that, again, as the colony is growing, and maybe that's a 15-year process to get to 1,000 personnel, as it grows, we're also developing manufacturing capabilities and value-added manufacturing capabilities on planet. And so eventually, an awful lot of the interior work, the modules that would go into finishing a space, would be more and more manufactured on the planet as opposed to imported from it. And I've got about 1 minute left. So it's getting close. I just wanted to mention this one. This was just another kind of expanded look at the residential concept. So again, the thought here is that it's got to be pretty compact. It's going to have to be high density. It needs to be very efficient. It's going to have to be communal in nature in order to fit within that square footage that we define. But there needs to be some diversity in private space if this is where you're going to spend your life. And so I came up with an example of what maybe an arrangement might be with the quad model. So 4 kind of small efficiency apartments with a shared great room, and then several quads would share a no-host kitchen space down the hall, something like that. And then the commercial centers, that's again to add the opportunity for social activities and some entrepreneurial activities, and those are integrated in with those residential sectors so people can move from one to the other and make choices. And I think that's pretty much it. My summary was to recap the system. So we took a look at the electrical energy systems, we took a look at the thermal energy systems, we took a look at the environmental systems that we thought would work well for this hypothetical NewMars colony. We looked at the construction approach and then ultimately what the solution is. And I think that's it. Yes.
Just while we're waiting for questions, can the next speakers, if they're here, start studying? Yep, you had a question?
Okay, in your how many acres per person type stuff, have you put in the fact that small people that consume less is a better bet than big people that consume a lot?
No, but you know, I did do a little section there on really the kind of upfront planning you would have to do with the group that's going to go and occupy NewMars as a colony. And there's going to be a large recruitment process. And if that turns out to be a desirable value, then it could certainly be rolled into the recruitment process. But we also envision, realistically, that NewMars is likely going to be it's not going to be devoid of children. There's going to be families that, if they don't initially go to NewMars, we're going to end up with families in fairly short order. And so you're going to end up with quite a mix over a generation of bodies that are consuming food production. Yep, I appreciate the question.
Great.